Hello and welcome back to the Aimless Electron. This video took a little bit longer to get out than I was planning, but life does get in the way, like Christmas, vacations, and catching a cold, which I'm still getting over. Anyways, this is the next part of the DIY Reflow oven project, and in this episode I decided to squeeze this in here real quick to look at an update to the hardware that I did, even though I wasn't really going to talk about hardware. This is just some components that I threw on there that I wanted to share with you. And then we'll take a look at the driver for the timer counter that's being used to clock everything in our project. Also probably take a quick look at some of the other drivers that we need software-wise for the peripherals inside the microcontroller and what it takes to get them to play nicely with ASF and the rest of what we're using. Anyways, let's go take a look at the hardware real quick. I didn't do a lot of changes to the hardware here, but one of the things I forgot to do earlier was put on these power filtering caps. Eventually I think I'll just solder on some SMD components between the pins on the breakout board itself so I never have to worry about them again. The next thing I added was this 1K resistor. I'm not sure if you can see it, but it's sitting between the positive voltage rail and the reset. That's mainly because this programmer, if it gets disconnected, will draw that reset low, and so this will keep it high and still allow the programmer to drive it low when it needs to if it's turned on, if it's plugged in. The last thing I added was this 1K resistor and this LED, just so I could have some visual feedback and to be able to hook it up to an oscilloscope easier. Right now I'm testing a 1 kilohertz frequency internally using the clock, which I'll show you in the software next, and then dividing that down by 250 so I get a 4 hertz wave out, and I toggle this LED on that 4 hertz so it actually shows up as a 2 hertz signal here. But you can still see that the pulse width is 250 milliseconds. Pretty stable, and that's exactly what we're looking for. So let's take a look at that in software. Okay, back in our DIY oven project here, we have the code for the main and this new line. This line basically sets the direction for pin 0 on port B. That's what our LED was attached to. The next thing I did was move the call to IRQ initialize vectors down. If you remember, all this does is turn on all of the interrupt vectors, low, medium, and high. In other words, it allows all those. The next thing I added was this call to init timer. Init timer is a function I'll show you in a second that I wrote that initializes timer counter C0. In other words, the timer counter 0 on port C. Finally, to support printf, I included the standard I/O and set the standard I/O as well. I'll talk about that last. Up in our timer counter, you have this new call to initialize, enable, or sysclock enable modules. The reason that's here is because when you actually initialize the system clock, it goes and turns off all the peripheral clocks for power saving mode. And all you could do is wipe this out if you wanted to, but I wanted to show you this just in case anybody else is running into this problem and can't figure out why something else that uses the clock isn't working. You have to enable it. Next we have our enable on our interrupt. So basically we're telling this clock that when it overflows our period, that it raises a low-level interrupt. I'll go over that next, but before I get to it I want to talk about this period and this clock divisor. This basically sets up our clock to be the peripheral clock and then divides it by 64. Or in other ways to put it, there is an output that's already divided by 64 from our peripheral clock, and that's what we're setting this timer counter to use. We're also setting our period to 750, and I'll explain why here in just a second. But just to let you know, we're using our clock in normal mode, which means that once it reaches that period, it causes an overflow, and that's what triggers this interrupt. A little bit of math. If you remember, we were actually overclocking this chip to 48 megahertz instead of 32. And why 48? Well, because our USB requires that. Now the chip doesn't glitch out and it doesn't get hot, so you can actually run it at that just fine. It just means you have to adjust some of your timings. In this case, we have to divide this down a little bit differently if we want 1 kilohertz. So the first thing we do is divide this by 64, because that's what our divider is, and obviously you can see this is 750,000. If we want 1 kilohertz clock, or a clock at every 1 millisecond, we got to divide this by 750, which we're doing. So we divide that by 750 and voila. Now let's talk about the interrupt real quick. This is the call for the interrupt. You set the interrupt vector handler, and I've got two things going on here. If you remember on the oscilloscope that we saw the frequency was 2 hertz for that pulse, well, that's because we're toggling pin out on every well, every time we go through this if statement. And we've divided the clock pulse, which is 1,000 hertz, by 250. So that means we get a 4 hertz output. This basically divides it by 2 again. That's how we get our 2 hertz output. And I'm also printing out hello world basically 4 times a second with this blink count. This is an integer, so it's 16-bit. And that means after 6,553 or 55, it'll finally overflow back to 0. But it's just a way to see it happening, which I'll show you in a second here. The last things I've added were some calls to set up the standard out. I had to add this function in here because the standard out, this fdev setup stream, looks for a signature with a character and a file pointer. And that wasn't in this one. It only took a character, so I just make a call to that. That's basically it on the software. I will put in here that there is a way to set up the USB without using ASF, but it is much more complicated, and I can do that in another video. Just let me know in the comments if you'd like to see that. For now, let's take a look at this thing working in the COM. Pretty simple. As you can see, every second it's spitting out 4 of these, and it's counting up. Very quickly, I want to take a look at the other software drivers that we'll need to write for the peripherals inside of our microcontroller. We've already gone over the USB CDC driver provided by the ASF, and that provides us communication over RS-232. And we just went over the timer counter that'll be used for system control for things like button debounce, or reading the buttons in the first place, reading the temperature sensor, or printing things out to the screen. The other things we'll have to look at is the non-volatile memory controller for flash for storing the profiles, and the non-volatile memory for the EEPROM for storing things like our font that we want to draw to our actual screen. We'll need SPI drivers for both reading the temperature sensor and for driving our little screen. And finally, we'll need some other GPIO, which you got a taste of with the blinking LED thing, for reading in our buttons and for controlling other LEDs. So that's it for this video. Hope you liked it. I know it was pretty short. I'm hoping to make these shorter anyways. In the next video, I'll probably talk more about handling the AT commands. If you like this video, give it a thumbs up. Let me know in the comments what you thought about it, or if you have any questions, or if there's anything you'd like to see me do. And subscribe so I know how many people actually are into these things. Also, I'll leave you with a picture of the modification I did by adding those surface mount capacitors to the breakout board for the Atmo controller. Anyways, see you in the next one.